Okay, section 1.2.1. We are now in the second section. There's actually going to be two parts today, 2.1 and 2.2. The 2.1 is about creating linear equations, and then 2.2, if you scroll down or flip the page, you'll see it's about creating inequalities. So, a couple things we've actually talked about before, right? So we talked a lot about expressions last time. Today we're going to take the next step into equations and inequalities. So let's try that out. Okay, we have expressions have algebraic terms, right? And you can set them equal to each other. That's the big difference for today. Last time we were making expressions. Expressions are just jumbles of algebraic terms, right? 4x plus 3, 75x plus 95, right? Whereas an equation actually has an equal sign. That's super important. An equation has an equal sign. It can be solved, right? You can actually solve this one out for an answer. Or you can graph it for a whole bunch of answers. So we're going to be creating equations today. Let's take a look. Let's just dive in. Example number 1. Andrew is practicing for a tennis tournament and needs more tennis balls. He bought 10 cans of tennis balls online and received a 25% discount. The shipping cost was $5.99. Let X represent the cost of each can. Write an algebraic expression to represent the total cost of tennis balls with the shipping cost and the discount. Simplify the expression. How much money will Andrew need if each can costs $4? Okay, so this is kind of a review from last time. We're going to build an expression. But as always, the first step is underlining, right? This is a huge paragraph. We do not want to deal with huge paragraphs. I don't know about you, but they give me a headache, so I don't want to deal with them. Maybe if I look at them, I actually get a little scared, and I don't want to get a little scared. So I'm just going to tackle it one sentence at a time. I'm going to underline, and then I'll feel much more better about myself. Okay, cool. Andrew is practicing for a tennis tournament and needs more tennis balls. That doesn't really sound all that important. It sounds like it's just trying to tell me what's going on. Okay, so I don't need to underline anything there. He bought 10 cans of tennis. 10 cans of tennis. Tennis balls, if you want to add. Sorry about that, typo. 10 cans of tennis balls. And he received a 25% discount. Okay. Shipping cost was $5.99. Usually shipping cost comes before the discount, which sucks, right? Because then you end up having to pay that whole thing back, right? I remember one time I had a shipping cost. I had a discount of 10% and a shipping cost of 10%. I was so mad. I called the company. I was like, really? You just took away the whole discount with this stupid shipping cost. It was so stupid. Anyway, so usually it comes after the discount, so we'll know that's got to play in somewhere. And then let X represent the cost of each can. That's nice. They told us what to define X as. That was something we were doing last time. Write an algebraic expression to represent the total cost of the tennis ball cans, with the shipping cost and the discount. Alright, so the total cost, that's what we're shooting for. Simplify the expression. How much money will Andrew need if each costs $4? We will come back to that question at the end, but it's important to remember it's there. Alrighty. Let's write down what important things you've underlined. 10 cans, right? He got 10 cans. That's good. Got a 25% discount. That's good. Let's see. Shipping cost was $5.99. It's actually a really cheap shipping cost. It must be in-state. And then they said they want X to be each can. Okay, so I want X to be the cost of each can. Alrighty, so now I've got 4 tiny little pieces of information, right, as opposed to this huge paragraph. I think I'm feeling a little better about myself. Instead of, instead of 5 sentences, I've got 4 things to consider. That's nice. That's very convenient. So let's start building this expression. Well, it's going to start around X, right? And X represents the cost of each can. Well, if Andrew is buying 10 cans, and let's say they were $1 each, how much would he spend? Spend about $10, right? If they were $2 each, they'd be $20, right? So it looks like every time, what am I doing? Let's see, $1 each gave me $10 for his cost. So we can write that down over here. $1 each gave me $10 for cost. $2 each gave me $20 for cost, right? So it looks like I'm multiplying by 10 each time. So it looks like X dollars for each is going to be 10 times my cost, right? 10 times X. That'll be my first part. So notice how maybe using real life examples can help you out if you're not quite sure where to start, right? Think about it. You've been in these situations. You've gone to the store. Whether you've actually bought stuff or you're just there with your mom, you know, whatever happens, you've seen this stuff happen. You've seen, I need 10 of these, they're $1 each, I better have $10, right? So you've done this stuff in your head. You just probably haven't used X before, right? So real life examples can help. Alrighty. Now we've talked about this once or twice before, last time, discount, right? So how would you apply a discount? So we did this part. Check. How would you apply a discount? Well, you can think of this one of two ways. We can think of this as the actual discount, or we can think about what we are going to actually pay. So let's think about this logically. If they take away 25%, how much are we going to pay? How much is Andrew going to pay? And percent-wise. He's not going to pay 25%. That would be awesome, right? Because that'd only be like $2, $2.50. But if he's going to pay, if they're going to take away 25%, he's going to pay 75%, right? So he's going to pay 75%. 75%. Andrew pays. All right. How do we make that into something we can actually put in the equation? Well, we can't put it in as a percent. Got to put it in as a decimal. So move 2 decimals over. 0.75 times the total cost, right? So they're going to take that total cost and they're going to times it by 75%, so that's all he pays. Cool. Now our total cost was 10x, right? That was our total cost. So we're now going to take this and we're going to multiply it by 0.7. Oops, ran out of room there. Just going to get rid of the C here. So we're going to multiply... Undo buttons are great until they're not. 0.75. We're going to multiply it by that 75%. Awesome. So he's got the total cost, the 10 times whatever each one was, right? $100 or whatever it is. And then he's only going to pay 75% of that. Now, as we talked about before, shipping costs usually come after discounts, which suck. So they're usually pretty constant, right? They're pretty constant at the end. And because they're pretty constant, they're going to be our constant. So this is going to be our constant, that plus $5.99 for shipping. Alrighty, and we have our expression. Let's go ahead and simplify this a little bit. Simplify it just a little bit. So looks like I can combine these two guys. So I have 7.5x plus $5.99 is what Andrew is going to pay for X cost of each can. Right? So if they end up being like $2, I can plug in 2 and I'll find out how much he's paying. Alright, any questions at all, make sure you pause, and then we'll answer the second question. After we simplified, they asked how much will Andrew need if each can costs $4. But if you have no idea where this expression came from, I want you to make sure you ask right now. Okay, so let's plug it in. We want to plug in the if each can costs $4. I need to know, should I make that like the equal to part? Is that what I'm plugging in? Is that what x is? Should I change one of my coefficients? Like, what should I do here? Well, if I look down at x, I said x represents the cost of each can. Now I know the cost of each can was 4. So they seem to coordinate, right? They coordinate very well. So it looks like x equals 4. So 7.5 stays the same. This time we're going to change x to 4. And then we'll still add on that shipping cost. All right. And when we do that, we end up with, let's put it in pink, $35.99. So 7.5 times 4 is going to be $30 plus the $5.99 shipping. That's how much he's going to need if he needed 4 cans, or if they were $4 each, pardon me. Alrighty. Any questions at all, make sure you get them asked. Otherwise, we're going to head on to equations now. Alright, so the steps for creating a linear equation from context. Remember, context means word problem, right? So everything is a word problem. We're going to set up this linear equation. This is what I'm going to start calling the general form of a linear. It's slope-intercept form, definitely. It's y equals mx plus b, and that's great. But when we have to think about word problems and stuff, I'm going to start using the pieces. Okay, so we've got some pieces here. So there's some things you definitely need to know. M is called our slope. You may or may not have heard that before. B is going to be our y-intercept. No, not y. B will be the y-intercept. Sometimes you'll hear x is the independent variable, y is the dependent variable. I probably won't, talk about that too much, but it happens. B is also going to be your constant. And slope is always going to be your coefficient. Right? Because if you remember, I mean, look, M is always the thing sitting in front of the X. It's a coefficient. B is always the thing by itself. It's a constant, right? So if I say what's the constant here, right, if you hear something that's be like, oh, that sounds very constant, then you know it's going to be the y-intercept. It's going to be the B, right? So it's important to remember your general form, what you're shooting for here, right? And if we saw that in the last problem, the shipping cost was B, or the shipping cost was constant, right? So the shipping cost ended up being the B part of our expression. So we're going to do the same thing. This time we're going to tack a y on it. So if you hear me call them stuff like this, just know that that's what we're shooting for, coefficient and constant, right? These are what we call parameters, by the way. Parameters. So the parameters are the things you actually plug into. Coolio. The steps for actually finding these are exactly the same as we've been doing for expressions. Exactly the same. Read the problem. Read it. Reread it and make a list or a table of known things, right? Make that list like we've been making. Define your variable. Read the statement again. It says to read it 3 dang times. It's really important. If you read it, it becomes less and less scary, right? If you pull out information you need and then you define your variable, you'll be good. Create an equation or an inequality. It happens to be an equality, whatever, right? And with known quantities and variables, so define your x's, right? Define your x, define your y if you need to, define m, define b. Then you go on and you solve the problem. So all of this, if you remember from last chapter, we called this translate. Translate. I ran out of room. Okay, we'll put it up here. Translate. We have to translate it into math, right? Next step 5 is solve. And then step 6, translate it back. Interpret the solution in the context of the problem. So this is just translate back. That's not just for linears, guys. That's for everything. Translate, solve, translate back. Any word problem you're ever given, right? Whether you're doing slope-intercept form, whether you're solving world hunger, whatever you're doing, right? Take the problem, translate it into math, use math, translate it back. That's really all it comes down to, okay? So you never have to worry about word problems. Or people always think word problems are so complicated. They're really not that complicated. Sometimes you have to, like, figure out what they're trying to say, but it's like an extra 30 seconds of brain power, and I know you guys have way more than that because you spend more than that on your phones. So just don't freak out whenever you see word problems. It's totally fine. All right, let's try one out. We're going to go for an equation this time. Example number 2. James earns $15 per hour as a teller at the bank. In 1 week, he pays 17% of his earnings in state and federal taxes. His take-home pay for the week is $460.65. How many hours did James work? 17 is actually pretty low, so lucky James. Okay, so we've got a lot of information here. Read it once. There's a lot of things here. There's not a lot of sentences, but you can tell. There's a lot of numbers going on here. There's a lot of things they're telling us that sound important. So let's go through and let's underline them. Let's see. James earning $15 an hour. That sounds pretty important. The fact that it's as a bank teller, probably not as important because we didn't hear anything else about bank tellers, right? In 1 week, he pays 17% in state and federal taxes, and then his take-home pay was $460.65. How many hours did James work? Okay, so notice I've taken this 4 whole sentences and boiled it down to 1, 2, 3, 4, 5 underlines of a few words. Much easier to handle, right? Even better, I'm going to write it over here. $15 per hour. 17% in taxes. Take-home pay, so take-home of $460.25. And then they want to know how many hours he worked, so I'm going to make that my question. I'm going to make X equal to hours worked. The only thing we have to be careful of now is that which variable are we defining here? So when we create an equation, we end up with 2 variables. Y equals 3x plus 4, right? Y equals 9x plus 5. You have to wonder, okay, are you worrying about x or are you worrying about y? In this case, I'm going to set up hours as y, right? Because Even in exponentials, x ends up being time most of the time. So since I know how much he worked and I know how much dollars, since it says per hour, right, very similar to what we were doing in 1.1.1 and the end of chapter 3 last time. I'm going to make x hours. I'm going to make the hours he actually worked. So that when we solve this, we're going to solve for x equals something. Okay, cool. So let's start doing that. Once again, check it out. I've whittled this whole mess of information down into 4 nice, easy items. And now I can use that to create an equation. So that was the translate part. Let's go, well, actually, that was part of the translate part. Let's go make an equation. That'll be finishing out our translation, our translation. All right, so I'm going to go ahead and do this now exactly like we just did the last problem. I'm going to take the information, we're going to translate it. Now, hopefully it ends up in this kind of form, right, because that's what we're shooting for. But let's just go piece by piece. Okay, so x. Let's start with the x. Right, that's the number of hours James works. Cool. What's going to happen every hour he works? He's going to earn $15 per hour. And just like we saw here with the each can 10, right, if he works 1 hour, he's going to get $15. Works 2 hours, he's going to get 30. So it looks like it's x times the number of hours he works. $15 per x hours. Good. Now from there, they're going to take away 17% of that, right? Because taxes, unfortunately, they take it away. They don't give you more, right? So they're going to take away 17%, which means he's only going to be left with 100 minus 17, right? So let's figure out how much he's going to be left with. So if they take away, he earns 100%. They take away 17%. He's going to be left with 83% of his paycheck, which is still pretty good. Still pretty good. And then as a decimal, that's 0.83, right? 2 places over. So he's going to only be left with 0.83% of his paycheck. All right. And then after that, his take-home pay is $406.25. Now let's be careful here. In the last problem, we had a shipping cost of $5.99. That was an additional $5.99. The take-home pay is not going to be an additional $460 as awesome as that would be. That's what it's going to end up being, right? That's what it equals. That's what his paycheck is. Notice these equal words that we're saying, right? So the take-home pay, this whole thing here is going to equal that $460.25. So his take-home pay is going to equal that. And we have our equation. We can simplify a little bit. 0.83 times 15. That's going to be 12.45 times x is equal to 460.25. So it looks like if he gives up 17% of his paycheck, he's losing about a little under $3. Little under $3 per hour. That sucks. So he's going to lose about $3. So he's going to make $12.45 now, which is fine, right? That's taxes. They pay for our road and whatever. And we end up with this kind of equation. So let's see if he earned this much, or let's pop our equation. So that's our equation. Oh, just happened. All right, so 12, 45, and 460 equals 460.25. Now let's figure out how much he actually worked, right? So how many hours did James work? Well, we can solve this equation. Notice it's so much easier to just solve an equation instead of sitting here like, okay, well, if he earned 15, then he paid this. If he worked 10, he got this. No, that's horrible. Don't ever do that. Instead, let's just divide by 12.45 to both sides. And we end up getting, so 460.25 divided by 12.5. We get about 36,96787 is what we have. So I'm going to round that up to 37 hours. So x equals 37 hours. And what we just did at the end, the 37 hours, that'll translate back. So here is our solve. We got x equals 36.9787, right? However, that sounds weird in the context of the problem, right? Maybe some computers are that technical, but we can round up and said, James worked about 37 hours. And we answered the question. We translated it back. All right. So that was our first equation. Let's try another one. I'm going to let you guys, actually, let's try this one together. No, I'm going to let you guys try this one. Let's read it together, though. Brianna had saved $600 to buy a new TV. If the TV she wants costs $1,800 and she saves $20 a week, how many years will it take her to buy the TV? Now read that very closely and look at the bold. So she's already got this $600. She wants to save up this $1,800. You guys try it out and solve the equation. Alright, so I hope you had a chance to try this one out. We're going to do it together fast. Brianna had saved $600 to buy a new TV. I'll underline that because it sounds important. The TV she wants costs $1,800. She saves $20 a week. How many years will it take her to buy the TV? Alright, so it looks like, she saved $600 already. The total cost is $1,800. And she saves $20 a week. Alright, so it looks like X will be the number of weeks. So X is going to be the number of weeks it takes her to buy the TV. She saves $20 per week, right? Same thing as the $15 per hour. And she already has a constant of $600. Right, so plus the $600 she has, that will equal the total of $1,800. And we have our equation. 20x plus 600 equals 1,800. So let's go ahead and solve that. We'll subtract, right? Start as far away from your variable as you can. We end up with 20x equals 1,200. Right? So 600 to both sides, right? Subtract 600, subtract 600. Now we'll divide by 20. We end up getting x is equal to, I want to say 60. Yep. X is equal to 6 weeks. Alright, and that's our solving part, right? Now we need to actually answer the question. So let's make sure we translate back correctly, right? It says, how many years will it take her to buy a TV? Ooh, good thing we double checked, because they didn't want the answers in weeks. They wanted it in years. So how many weeks in a year? Well, there's 52. So we have 60 weeks times 1 year over 52 weeks. Looks like we're going to be dividing 60 by 52. And we get 1.15. So 1.15 years. That's how long it's going to take her to earn this TV. If she saves $20 a week. It must be a pretty nice TV. Sounds pretty cool. Okay. Let's head over to example 4 now. If you have any questions, make sure you get them answered. But let's keep on. Suppose two brothers who live 55 miles apart decide to have lunch together. Wow, that's a lot of miles apart for lunch. To prevent either brother from driving the entire distance, they agree to leave their homes at the same time, drive towards each other, and meet somewhere along the route. Older brother drives cautiously at an average speed of 60 miles per hour. The younger brother drives faster at an average speed of 70 miles per hour. How long will it take for the brothers who meet? Remember, distance equals rate times time. Okay, so it looks like we're going to be using this distance equals rate times time, but let's start with underlining. They live 55 miles apart, sounds important. The older brother drives 60 miles per hour, so let's underline older. And the younger brother drives 70 miles per hour. How long will it take for the brothers to meet? Okay. Well, there's a lot of information going on here, and it all centers around this distance equals rate times time. So let's go ahead and set up a little chart for each brother. Talk about distance. Actually, don't put distance there. Put distance there, rate there, and put time there. And we'll do brother here. So we've got older brother and younger brother. We'll come back to distance because they're not both going to travel 55 miles apart, right? They're going to travel, some distance, but we'll come back to that. The rate we know for the older brother was 60, and the rate we know for the younger brother was 70. Alrighty. They want to travel the same amount, right? They're going to travel the same amount. So they're both going to travel t time. We don't know that amount, right? We'll just call it t. Or we're just going to call it t. Okay. Now let's go back to distance. Well, distance equals rate times time. So for the older brother, it's going to take him 60 times time, and he's going to go 60 t miles. Do the same thing for the younger brother. He goes 70 t miles, right? So we just use this distance equation to create a little expression for each of them. So the 60 t, the rate times the time, is the distance. The rate times the time is the distance. Okay. Now, they do live 55 miles apart, so this together is going to be 55 miles, right? Together it's going to be 55 miles. So let's set up that equation over here. The distance the older brother travels plus the distance the younger brother travels is eventually going to be 55 miles. And we have our equation. So sometimes a table can be super helpful instead of a list, right? Sometimes a table makes life easier to see, right? If you've got multiple situations going on, sometimes you can use a table. And that's your choice. You could have done this in a list as well. We would have got the same equation. But for this one, I liked the table. Okay, so let's actually solve this now. We translated. Let's solve. It's going to be 130t equals 55. I just combine those like terms. Divide by 130, and t is equal to 0.42 hours, or 0.42 divided by 60, oops, or 2 times 60, pardon me, times 60 minutes in an hour, about 25 minutes, 25 minutes each. We'll just go with the hours though. And we also translated back by writing those units down. So each brother travels almost half an hour to get to the other one. Sweet. Alright, notice that in the last couple problems, we keep converting units over and over and over again, right? And that's an important part when you're dealing with stuff like word problems, right? When you're dealing with real life. You want to make sure you're in a scenario that makes sense. You're in units that actually make sense. If you're talking about gallons of paint for an entire apartment building, you don't want to be doing it in milliliters, right? That would be insane. So let's talk about a few situations real fast, about a few situations where what kind of units you use. So in example 5, it says, think of the following scenarios. What units should they be reported in? Explain the reasoning. We'll just kind of explain it together, and then you can just maybe make a note. Water filling a swimming pool. Well, what would be some good things for a swimming pool, right? That's a pretty big area. I don't think I want to do that in milliliters or in, drops, anything like that. Maybe gallons would be good. Or liters, if we happen to be in the UK, right? Liters might be good. I don't think I'd want to go so far as like the bigger one, like some super big ones, 100 million gallons or something like that. But I think gallons or liters are probably good. Okay, cool. Let's do number 2. The cost of tiling a kitchen floor. The cost. Okay, the cost, probably not going to be in cents. Probably not going to be in millions. If it is, then my goodness, what kind of tile are you putting in your floor? Let's just say dollars. Dollars is probably a good one for that, right? The effects of gravity on a falling object. The effects of gravity actually has a cool units. Gravity is meters per second squared. That's acceleration. Meters per second squared. There's also meters per second is velocity. So it's something per something, right? It's kind of like hours, $15 per hour. Right? So you're falling 75 meters per second. And then the per second squared part comes from acceleration. You'll learn about that in physics. But it's mostly just the meters per second. A snail traveling across the sidewalk. Do you think you want to measure that in miles? Probably not a good idea, right? But I think inches might be a good one. Or even centimeters, right? Depending on how scientific you are. Millimeters, even, if you wanted to be super accurate. Maybe you're only measuring them for like 10 minutes or something like that. You want to see how far it goes. So the smaller increments, right? And then painting your room, we kind of talked about painting a whole apartment building. You don't want to be doing it in milliliters. But painting, you could probably do it in, if you're looking at the paint, you can do gallons. But if you're actually painting, you'd probably look at hours or minutes. Minutes might still be a little big. If you're a really big area, you can look at days, how many days it's going to take to paint you. But you probably want to go with hours. So notice each of these situations had things that made sense and things that didn't, right? So things that would be weird. So if you're solving, if like back here in the Brianna problem, if you're solving things in a number of weeks, that's fine. Just make sure at the end you actually convert to what would make more sense. Looking at 60 weeks, you may think, okay, she's only got a little amount of time, but that's a year and almost a half. That's a year and almost a fourth, right? So that's a lot more time when you put it in years, right? So watch out for things like that. Okay. Let's see. We're going to do number 6. We're not going to have time for number 7, just because, for time, to be honest. We have another section to do today, and I want to make sure we get to that one. So let's do number 6, and then we'll head on over to 1.2.2. Ernesto built a wooden car for a soapbox derby. He is painting the top of the car and the sides black. He already has enough black paint and needs to buy blue paint. He needs to know what approximate area of the top of the car to determine the size of the container of blue paint he should buy. He measures the length to be 9 feet and 11 1/4 inches, and the width to be 1/2 inch less than 3 feet. What is the surface area of the top of the car? What is the most accurate area Ernesto can use to buy his paint? Okay. Lots and lots of information there. In fact, there was so much information, I don't even want to try to solve this before I underline stuff. Not even going to try and think about that. Alright, Ernesto's building a wooden car for soapbox derby. That doesn't sound super important. He is painting the top of the car, and the top blue and the sides black. He already has enough black, but he needs to buy blue. Okay, that's 3 whole sentences that I underlined nothing, right? I underlined nothing because it didn't give me any vital information to solving the problem. It just kind of helped me set up what was going on, right? So it's 3 whole sentences. I didn't have to do anything. He needs to know the approximate area of the top of the car to determine the size and container of blue paint he should buy. Again, a 4th one. That's just leading. It's just telling me what I need to do, right? It's telling me what we're shooting for. He measures the length to be 9 feet and 11 1/4 inches. There's finally a piece of information that sounds useful. The length is 9 feet and 11 1/4 inch. The width to be 1/3 inch less than 3 feet. Alright, what is the surface area of the top of the car? What is the most accurate area Ernesto can use to buy his paint? We'll come back to that. Alright, so it looks like we got length is equal to 9 feet, 11 1/4 inch. By the way, a soapbox car is not one of those little model cars. It's one you actually get in, so it's okay that it's 9 feet across. The width is 1/2 less than 3 feet. Okay. Lots of different units going on here. This is going to be nearly impossible to figure out an area for, right? Let's put it all into inches. Let's put it all in inches, okay? Since we don't have whole inches here for everything, right? We have 1/4 of an inch. Wouldn't make sense to put everything to feet. Let's take everything and put it into inches. So let's start with length. Length says we have 9 feet already, right? And how many inches would that be? That would be 9 times 12 inches, or 108 inches. Then I'm going to add another 11.25 inches, and my length ends up being 119.25 inches. That sounds like a much more workable number, right? Yes, it's bigger, but it's not 9 feet and 11 1/4, right? So that sounds a little more easy to work with. Let's do the same thing for this one. Let's be careful though. 1/2 inch less than 3 feet, and I definitely should have put inch in there. 1/2 inch less than 3 feet, so it's 2.5 feet, right? Watch those units. 1/2 inch is about like a quarter of your thumb. Like a quarter of your thumb. And then 3 feet is a yard. 3 feet is like part of a football field, right? It's a yard of a football field. So we're not taking off a whole 1/2 foot here. We're taking off 1/2 inch. So let's put these both into inches. The 3 feet would be, 3 times 12 would be 36 inches. Minus 0.5 inches. That's going to be 35.5 inches. That's still pretty close to 36, right? So he's not taking off much, just 1/2 inch less than 3 feet. Okay, we put these into similar units. Much easier to work with. Check that out. Now let's see if we can answer the question. What is the surface area of the top of the car? So surface area comes down to a formula. Area is equal to length times width. Hopefully we knew that. If not, there you go. There's a reminder. If area is equal to length times width, and the length is equal to this, width is equal to that, then I can plug in. I can translate into my problem. Translate here. Area is going to equal 119.25 times my width, 35.5, right? And that'll be my area in what? What units would be on that? It would be inches, right? So area, this is my area in inches. That would be an area 119.25 times 35.5 would be 4,233.375 inches squared. Inches squared. So I multiplied inches by inches, it gave me inches squared. Well, that's great, but again, let's translate back. Do you really walk around saying, oh, this soapbox car is 4,233.375 inches squared? No, you don't. You talk about feet squared, right? You talk about feet. So let's take this and put it into feet squared. Now notice, when you say feet squared, that means you're dividing by 2 times feet, right? So in this case, we wouldn't divide by 12, we divide by 12 twice, or 144. That would give us around, divide that by 144, 29.4 feet squared, right? So you do this, use the squared. You get 29, it's about 30 feet across, right? About 30 feet across. All right. So he needs about 30 feet of paint. Sorry, he needs 29.4 feet of paint. I kind of just answered our last question. The last question is, what is the most accurate area Ernesto can use to buy for paint? He can use that as the most accurate area, right? But is that really how he's going to buy paint? Is he going to walk in the store and go 29.4? No, he's going to say, you know what, I need about 30 feet of paint. So the most accurate he can buy at the store, you can argue that it would be 30 feet of paint. But if you wanted to get technical, he could tell somebody, okay, look, this is my area. I need enough to fill this in. So he would still probably end up buying 30 feet of paint. Alrighty. Remember, we're not going to do number 7. Not that you can't, it's just we're running out of time and we have a whole nother section to do today. So we will not do that one. We talked about a lot in this section. We talked about units, especially converting those units, setting up linear equations, right, using the same kind of tools that we used from context here. And we talked about setting up expressions, which we just did last time. We're going to head over into 122 now. But if you have any questions at this point, please make sure you get them answered. And I will see you then. Just